We are making hopefully best large language model in the world. It works on one GPU here, publish your own LLM. Now let's learn to scale it. This will split our model from one GPU only to two or more GPUs. Let's say you have input or activations X and weights W. You want to get output or activations Y. The first thing we will see is how to calculate this row on one GPU and this row of Y on the other GPU. If I scroll down, we see that we copy input to both of the GPUs. And then one column of this Y, so this first column, we multiply input on one GPU, and the second column, 30, 40, we multiply this input. And here, this result will be the first column, and this is going to be second. This is called column linear or column-wise tensor parallelism. Then we have row parallelism. Here we split W into rows instead. Now check this trick. This upper row of W will always only multiply this first column of X. You can try. So the matrix multiplication is like this. 0 times 10, 1 times 20, and then 2 times 10, 3 times 20, 2 times 30, 3 times 40. So you notice that numbers or elements from this column only interact with elements from this first row, either this one or this one. That's why we will split this first column, put here, and it's gonna multiply with this. And the second column we'll put here, multiply with the second row. And this also makes computation possible because this is 4-2 shape, but this is 1-2. We need to have inner dimensions same. So we need 1 here. So now if you multiply these rows and these columns, you're gonna see that you got this matrix. And in the end, we need to add them up. Because if you think about it, when we multiply this row and this column, if we separate them, then we just multiply this and then separately 1 and 20, and we need to add them up in the end to get this here 20. That's why we have this all reduce or adding up. How does that apply to a transformer and LLM? We know that LLMs are made of feed-forward multi-layer perceptron and multi-head attention. You know that feed-forward network in transformer has some input and then expansion to some hidden and then another output. So we have 2 times matmul with different matrices. So input X times some weights, we get hidden, the first activation, and then that times some other weights, we get output. So that's why we have here 2. We use column linear mat multiplication to go from input to hidden, and then row linear or row parallel to go from hidden to output. This is the best trick, the fastest with least amount of computation. Because here we don't need to synchronize, we don't need to send data from any GPU to the other in between. So we can just go from X to output without communicating between GPUs. And by the way, in the actual training, we will also already have these X's inputs at different GPUs. So we will not have start from 1 and then multiply, but we will already have them. And then multi-head attention, we can just split different heads onto different GPUs because heads are already independent. In this image, the top GPU is gonna handle set of attention heads, let's say 0 to 7, and the other one is 7 to 15, 8 to 15. So here we will have same input X, but this part of heads has its part of key query value matrices, and then the second part of the key query value matrices is on this GPU. Then we have this softmax dropout, and then with value. So all of the heads operate independently. That's why we can separate them onto GPUs. So in the end, we are projecting all of the heads onto a single output vector, which is going to be this all reduce. So each GPU will calculate its part of the output. So this B1 is its part or half of the output weights. And Y1 is these heads concatenated. So this here will be row linear or row parallel. You see that you have all reduced, so you are just adding this to this. Here, this is what it looks like. This is first part of the heads, second part of the heads, first rows, upper rows of the output matrix, and then lower rows. We get these two and then all reduce, add them up. And then we copy this final vector onto both GPUs. We apply dropout maybe. So when splitting, you want to split the number of heads. You don't want to have more splits than the number of heads. Let's go back to multilayer perceptron to see some issues. So at these dotted lines, we split our computation onto two GPUs. So this part. And then here we have all reduced where we are gathering information. So when we are gathering information, we cannot do something else. The next thing on the GPUs, we need to wait for the information to gather and all add up. And then we need to use this next. So before that gathers and adds up, GPUs cannot do the next thing. They need to wait for the result so they can continue working with that result. So that's communication overhead. That's just because we have multiple GPUs. Now we have to do this extra thing that we wouldn't need to do if this was on a single GPU. So this is the overhead. We hit a synchronization point with the all reduce operation that cannot be overlapped with computation. That's a weakness of tensor parallelism, where if we need to apply layer norm or some other operation that requires entire tensor, then we need to combine it from different GPUs. While if we had data parallelism, we would have full copy of the model on each GPU, so we don't need to combine these intermediate operations. Critical path is the sequence of operations that will give you minimal time required for forward pass. So this all reduce is in the critical path because it cannot be left out, and we have to get the minimum time with this. We cannot exclude it. So you use tensor parallelism, that is splitting the model onto multiple GPUs when you have a lot of compute but you lack memory. Look at this. We split model onto 2 GPUs, 4 GPUs, 8, 16, 20, 32. And the more GPUs we have, the more synchronization we need and this overhead. So tokens per second are going down, but your maximum batch size will increase with more GPUs because you can simply divide this batch amongst more GPUs. So if you go from 2 GPUs to 4 GPUs, now each GPU will be 10% slower. And then to 8 will be 12% slower than 4. And you see here the performance drops. So this looks like a huge performance drop. So I think 2 GPUs is good. If you train a small model, maybe 3-4 billion parameters. But if you train 300 billion, then you need to split it more. Also, maybe we can make this a lot better here. Maybe we can optimize so the performance here is better. What happens here is you have 8 GPUs in a single node that are connected with the fast NVLink. But when you start splitting it to multiple nodes, then the communication becomes a lot slower without the NVLink. And here I think it spends more time communicating than computing the results. That being said, tensor parallelism provides important benefits for memory usage by distributing model parameters, gradients, optimizer steps, and activations to some extent across GPUs. A lot of the time you would fit a large model onto a node of 8 GPUs, and within node those 8 GPUs are connected with very fast NVLink. There are some tricks where we can compute things that require syncing without syncing. So layer norm and dropout. For example, in dropout, we can just synchronize the random seed in the beginning of the training. So this will work as intended then. That will be it for this video. You can check other videos on my channel where we built the best LLM in the world, I hope, hopefully, and it's all gonna be open source and you will be able to contribute soon as I figure out research path. So see you next time.